Okay, so we just talked about ridge regression, or L2 regularization, or Gaussian priored linear regression. Let's look at another type of regularization in the context of linear regression. But let's start by asking the question, what if we want to perform feature selection on our input data? That is, we want to find a small set of features that are useful for our prediction problem and not necessarily use all of the features in our prediction. This is very often something that's of interest because in most prediction problems, most of our features are not relevant. Usually it's the case that there's some small subset of our features that are actually relevant for our prediction problem, and a big part of our task is we want to know which those features are. And there's kind of two aspects to this. Question number one is, can we use feature selection to improve our prediction accuracy? Because if we could, in the perfect world, if we could perfectly figure out which are the features that contribute and set all of our other weights to 0, that would greatly improve our prediction performance, because that greatly reduces our ability to overfit. Because we're fitting with a much smaller number of features, we have a much smaller number of weights for our prediction. So goal number one is just to improve prediction performance. Goal number two is often we're interested in knowing what those features are, because let's say we're in a biological application. If we want to know what are the features that are predictive of someone developing disease, we'd be very interested in knowing what those are, because that might suggest what aspects of someone's diet or behavior or whatever one might look to change in order to perhaps stop them from getting disease. So we have kind of these two goals in doing feature selection. So one way to do feature selection is we might add this a regularization term that looks like this. So this is not going to be the one we're going to use. This is kind of idea number one. But here's the first idea. We put on this term, which says we're going to add to our loss a term that goes over our d dimensions and gives us some penalty if the weight is not equal to 0. And so that is, we're preferring weights that are equal to 0. From kind of a generative perspective, we're applying a delta prior to W. So there's a prior that looks like this, just a spike over W. And of course, we'd want this value here to be non-zero. Otherwise, if we put all of our probability on 0, then it would just, of course, be 0. So this is idea number one. This is called the zero norm for reasons that I won't get into. But the zero norm is not what we're going to focus on for reasons I'll talk about in a minute. What we're going to focus on instead is putting a Laplace prior on W. That is, we're going to imagine that each Wi is distributed according to a Laplace distribution with mean 0 and Laplace parameter 1 over lambda. So this is this distribution, the Laplace distribution, is one that goes according to exp of minus lambda absolute value of d. So another way to write this is we want to minimize the one norm of W, which is the sum of absolute values of W. I should have, by the way, have written D here, just to be consistent with notation instead of I. I'm going to talk in a minute about why we'd want to do this thing. That is why we'd want to put on this Laplace prior or L1 regularization. But first, let's ask what happens from an optimization perspective when we do this. Now, the bad news is that unlike in the case where we had a one-step analytical solution for linear regression, we don't get that anymore for our Laplace prior, which, by the way, is called Lasso. I forget what this stands for. The L is for linear. In any case. So bad thing number one is we don't get an analytical solution. Two is that it's a little bit tricky even to use a gradient-based solver for this, because notice that we have a term that looks like absolute value of WD, which looks like this. Now we have this sharp point here, this function is not differentiable at WD equals to 0. So a lot of our simple gradient descent and things like that aren't going to work easily on this, or at least not right out of the box, on this objective function because it's now undifferentiable. We've also lost strong convexity. So recall that a function is strongly convex informally, we're not going to define this formally, when it is curved upwards. And so it's convex if it's not curved downwards, but it's strongly convex if it always has this upward convex curve. Notice that here our curve is, this line is straight, so this function it's still convex, and in fact there is a global optimum. I don't think I said this explicitly, but there's been a global optimum for all of our linear regression models so far. So it is convex, but it's no longer strictly convex, at least in general. Sometimes for a given problem could happen to be strongly convex. But it's not necessarily in the case of Lasso. So those are issues with optimization. So we're going to back up and talk about two optimization concepts before we're going to be able to do our Lasso optimization. The first is coordinate descent. So coordinate descent is a optimization method. We can kind of put it in same category as the various optimization algorithms we looked at, like the first order and second order and analytical optimization algorithms. Coordinate descent works as follows. At each update step, we optimize with respect to a single parameter. So in the case where our loss is a function of a full weight vector W, at each coordinate descent update step, we're going to set WD equal to the argmin in just WD. So that is, we're going to leave all the other parameters fixed and find the minimum just with respect to WD. So this is usually a good idea in the case where you can find a closed form update with respect to a single parameter, but you can't necessarily find a closed form update in all the parameters. So in the case where you have closed form updates in each parameter separately, this is often a very effective strategy. And in fact, that's what we're going to use for Lasso L1 regularization. if you can't get a closed form update with respect to each parameter, sometimes this is still a good strategy if at least you can get a extremely fast iterative update. That is, maybe you can use a second order method that converges in just a few steps. You'll see that used sometimes. But it better be that update is much faster than what you'd get from some algorithm that applied to the whole objective in all the parameters. Because of course, even once you finish an iterative update in a single parameter, you still have to do that again for all the parameters. And then, by the way, you don't get to do one pass of this. You have to iterate the updates until they converge. So a common way to do this is you can go through the parameters in order, go through them all, and then start again at the beginning. There's some acceleration methods for coordinate descent that try to choose which parameter to update next based on some guess about which is going to have the largest impact on the loss and which is going to bring us to our optimum fastest. We're not going to talk about those. So let's just focus on the case where we use some arbitrary order of the feature updates or parameter updates. The next idea we need to consider before we can do our lasso optimization is the idea of a subgradient. So as I said, our absolute value function is not differentiable. It has this undifferentiable point here because it's not continuous at that point. So a subgradient is kind of a generalization of a gradient or a derivative in the case of a non-differentiable function. So, and we're not going to go into a lot of rigor on subgradients here. It's a interesting topic, especially for optimizing cases where there's lots of undifferentiability or lots of undifferentiable points in a particular optimization problem. Here we have a pretty simple case, so we're going to have kind of a surface level understanding of subgradients. But a given gradient is a subgradient at a given point if the linear approximation of that function stays below the true function. Now, note that there are many gradients that are all subgradients at this point. So instead of, in the 1D case, instead of a single slope, we're going to get a interval of slopes. We're going to say that any slope between A and B, which in the case of the absolute value at 0 is going to be between -1 and +1, any of those slopes are all subgradients. So we can write the subgradient as this full interval of A to B. So this is going to let us optimize in the case of this undifferentiable function with a little bit more rigor. Okay, now using what we have so far, now let's do our optimization for the lasso problem. So we're going to use both of those tricks. One is to do coordinate descent. So we're going to do the optimization in just one parameter at a time, and we're going to make use of subgradients. So let's start with the no regularization case. So we're going to look just at our negative log likelihood in the unregularized case, and let's take the partial derivative with respect to a single parameter WD. So it's not, we're not going to prove this. We might give this as a homework assignment. But it's not hard to show that this is the partial derivative with respect to WD. It's this thing here. It's a linear function of WD. We have AD, WD minus CD, where AD and CD are defined as follows. So we have this thing which depends just on x, and CD is this thing that depends on x times the difference between yn and this thing here. So we're writing w minus d as the vector w with all of its dimensions except for d. So if we had a big D dimensioned vector w, this thing would be a d minus 1 dimension vector. And we do the same thing with x. This is xn minus d, meaning xn where we just removed dimension d. And again, it's not too hard to show that, that this is the partial derivative. Okay, so now, given that this is the partial derivative, we can set it to 0 very easily. We just get that WD equals CD over AD. Here, we've written this in kind of a condensed form, where we defined R minus D as, again, the residual. That's kind of like this thing here is RWD, or R minus D. That is our error when we have D missing. Okay, so that was the case where we were looking at just normal linear regression. So now let's see what happens when we add in this Laplace prior L1 regularization. So here again, I'm not going to derive this, but it's not hard to do. We have the partial derivative with respect to WD of now our objective, including that prior. Same as before, we're going to end up with that term that we get from our main objective, and then we get an extra term that comes from our prior, which is just lambda times the partial derivative with respect to WD of the L1 norm of W, which this thing is just the derivative of absolute value of W. So now note that this is going to have subgradients, not necessarily a derivative, because it's not differentiable, because it's not continuous everywhere. So we can see that if WD is less than 0, then our subgradient is going to be a single point. It's just going to be this thing here, or this thing here. This term plus lambda times WD is negative, so this is going to be a negative number. Vice versa, if WD is positive, again, same thing. The function is differentiable there, so our subgradient is just a single point. Now, the only tricky part is in the case where WD exactly equals 0, we're going to get a subgradient that's a interval, which is the following interval. Note that this term here went away because we're assuming that WD equals 0. So we have minus CD minus lambda is the range. The range goes from minus CD minus lambda to minus CD plus lambda. So that's our subgradient for this function. So we need to take the derivative. Now, how do we optimize with respect to this derivative? So based on this, we can see that we can find the optimum with respect to W, that is, our gradient equals 0 if we set, if we have to compare CD and lambda. So if CD is less than negative lambda, that is, if CD is a strong negative number, we can think of CD as like the correlation between this feature and our response, the thing we're trying to predict, our label. If CD is a large negative number, then we set our weight to CD. The normal thing to set it to would be CD over AD. Instead, we're setting to CD plus lambda, so it's a less negative number than it would be overall. Vice versa, if CD is a large positive number, we set it just to what we would before minus lambda. But if CD is within this range, then we just set it to 0. So one way to think of this is with this plot. So this is what we're going to set our W hat to as a function of CK. If, again, if the textbook switches notation here, we're using K here instead of D, but otherwise this is the same thing. If, again, if here's this line is our normal update for normal linear regression, with our L1 regularized lasso, we get instead this line. So if CD is a large negative number, we set it to that value plus a little bit. Vice versa, if it's a large positive number, we set it to that value minus a little bit. And if it's anywhere within this range, we set it exactly to 0. Okay, so that's our update for our lasso optimization. So the normal way to do optimization for lasso is we use our coordinate descent update. So we go through one parameter one by one and do this update here. Notice this is a closed form update. It's very fast to compute, so that's good. We go through one by one, starting over once we get to the end of our list of parameters, and we do that until we converge. And that will give us a global optimum if we converge for our lasso optimization. Again, this problem is convex, so we don't have to worry about multiple optima. Okay, so let's go back to that question that I left off at the beginning, which is why would we want to use L1 regularization, aka Lasso, aka Laplace prior linear regression? Why would we want to do this in the case where we're interested in feature selection? Because on its face, it's not obvious that L1 regularization would cause us to do feature selection. That is, we're putting what seems like kind of a smooth penalty on high values. That is, we're not doing L0 regularization that I posed at the beginning, where we just put on a flat penalty as long as the weight is non-zero. It seems like L1 regularization ought to just give us smaller weights, not necessarily give us 0 weights. So I think it's important to think a little bit about why it is that L1 regularization gives us 0 weights, and why we wouldn't want to do L0 regularization. So the main reason that L1 regularization is very widely used and L0 regularization is almost never used is that L0 regularization is very difficult to optimize. So if we look back at that L0 objective function, where we put a penalty on non-zero weights, notice that this thing is, again, it's not differentiable at this point. That's the same problem we have with L1 regularization. But it's also non-convex. So we can get local optima very easily. And none of our gradient-based methods are going to work. And it's easy to see why they wouldn't work, because according to the function's gradient, there's kind of no way to know if I'm sitting here that I would want to go in this direction and set the weight all the way to 0 in order to get a big boost in my, or a big reduction in my loss. So again, L1 regularization is very challenging to optimize. L0 is very challenging to optimize. I'm not sure if I said the right one just then. And in fact, we can be a little bit more rigorous about this. Let's imagine the class of Q norms. So this includes L1 and L2 norms. So it's not too hard to look at this expression here. I've written this expression as the sum over D of the absolute value of WD to the qth power. So in the case of a 2 norm, Q is 2, to the power of 1 over Q. So in the case of Q equals 2, this is Euclidean distance. In the case of Q equals 1, this is that Laplace prior or L1 regularization, or our L1 norm, term that we just saw. It's not too hard to show that as Q goes to 0, we get the 0 norm here. And in fact, you can show that the smallest Q for which the Q norm is convex is the 1 norm. So any smaller and you get a non-convex problem. One motivation for picking the L1 norm for L1 regularization, if we want sparse solutions, that is, if we want to do feature selection, is that it's the closest to the 0 norm we can get while still maintaining a convex optimization problem that we can optimize efficiently. Okay, so that's kind of reason number 1. Reason number 2 we just saw. So why is it that a L1 regularization gives us sparse solutions? Well, we can kind of see it in our optimization. So our optimization step, notice that there's this large range of C for which we give ourself a weight of 0. So in some sense, this is different than the case where we have just our normal linear regression optimization. You can see that only when C is exactly 0 do we also set W to be 0. In the regularized case, there's this big range from negative lambda to positive lambda where we set W to 0. So we can kind of see from our optimization why, when we apply that optimization, we end up with a lot of zeros in our optimized parameters. Another way to look at this is with kind of a geometric perspective. So here I've drawn here's in these red level sets, we have our standard linear regression objective function. And let's look on the right to start. This circle is the set of points with a L2 regularization loss less than some value. So it's not too hard to show that once you apply L2 regularization, your solution is gonna lie on the intersection between this ball and a level set of your objective function. And the question is, so this thing here will be our chosen W. And the question is, where is that chosen W going to fall in space? So notice that here it's fallen at a point where both W1 and W2 are non-zero. Now if we go over on the left to the L1 regularized case, notice that the level sets of the L1 regularizer form a diamond. That's not too easy to, or not too hard to convince yourself of. And we can kind of see how any given objective function is sort of more likely to intersect at the corners of a diamond, because in kind of a geometric and intuitive sense, they stick out more, and so they're more likely to be the spot where you intersect. So this is kind of a geometric interpretation. Maybe this is useful to help you understand why L1 regularization ends up giving you sparser solutions, is because you're likely to intersect at the tip of this diamond, and that tip corresponds to a position where one of the parameters, in this case W1, equals 0. Okay, let's ask about our variable selection consistency. That is, let's assume that there's some small subset of our features that are the true features that influence our outcome, and that in fact the label is a linear function of those features, and kind of all the other features are just contributing noise. By the way, I should say that everything we're talking about here with regards to L1 and L2 and L0 regularization, pretty much all of these things hold for all methods, including linear regression as well as logistic regression, and any other kind of more complicated model you might think of. But we're focusing on linear regression because it gives us a nice kind of test bed to see the results of these decisions. Okay, so one thing to be aware of, let's say we choose our L1 regularization weight using cross-validation. That is, like I showed for L2 regularization, we do a plot of the training error, which is going to increase with respect to the regularization weight, and the test error, which is going to have a U shape. And let's say we choose the regularization weight that minimizes the test error. So we do expect this to be U-shaped because, again, just like in the L2 regularization case, our lambda helps us trade off the complexity versus expressivity of our model. So with a very low lambda, we should write this as minus lambda or 1 over lambda. With a low lambda, we're going to end up likely overfitting. But note that in most cases, we end up with less sparsity than we would like, just choosing lambda according to cross-validation. One reason for that is that remember that when we do our optimization in the presence of our L1 regularization, we both set some parameters to 0 because of it, and we also subtract lambda from everything else. So now because of that subtraction of lambda is kind of hurting our modeling power, and therefore cross-validation is going to end up choosing a relatively mild value of lambda, and therefore a relatively minor amount of sparsity in order to optimize our prediction performance. So often when we're doing feature selection, and especially in the case where we're actually interested in what features we uncover, not just in using it to improve our prediction performance, usually we'll choose a higher lambda, a stronger lambda, more regularization than cross-validation itself would tell us to. Let's look at an example to see how this works in practice. So this is some synthetic data where we have defined some true function. So the observed label is in fact a linear function with the weights defined here. So we have a vector of 4,096 features, of which 160 are non-zero. And we can see this is the full 4,000 dimensional vector, and the weights are either +1 or -1. And you can see that a lot of the points here are 0, meaning that it's a very small fraction of the features that in fact have non-zero weight. So first thing, let's just go to our ordinary least squares solution. Here are the weights we get from that. So notice that there are very few zeros in this vector, maybe no zeros, and in fact, so we're not doing really any feature selection. We're not choosing a subset of the features to choose as the ones that contribute to our prediction. Okay, now what if we use L1 regularization? We get the following. So it's not too hard to see, just kind of from visual inspection, that, well, number one, that this is in fact a sparse solution. That is, there are very many zeros in this weight vector. And in fact, it's the case that the weights match up pretty well with the true weights. But we can see something here, that the weights tend to be lower. And that's because of this biasing that's introduced by the L1 regularization. Because remember that in our L1 update, we don't just set some values to 0, we also subtract lambda from all of our other weights. So we end up with weights that are a little bit smaller in magnitude than they would be otherwise. So this plot number 3 is something that's commonly done. So this is a way to try to get the best of both worlds. We know that we can't optimize the L0 norm because it's not convex. We can't do it computationally efficiently. But we can kind of get close to it. The way we do this is we first do L1 regularization to find a set of weights with non-zero, or a set of parameters with non-zero weight. And then we redo our optimization. We throw out all the other features and give just those features, and then we do unregularized optimization. So here what we get when we do that, you can see, so this is sometimes called debiasing because it's removing the bias that's introduced from the L1 regularization. So we can think of this as kind of an L0 norm because we're forcing all the other weights to be 0. Of course, the model doesn't even get to try assigning those to have non-zero weight. So this is not in general going to give us as good a solution as if we could somehow try all possible subsets and evaluate the performance of each one. Again, that's not computationally feasible. But you can see that when we do this debiasing, we end up with weights that are a little bit larger in magnitude than the ones we get from this normal L1 regularization. So this is often a good thing to do, especially if you're interested in feature selection. Do your L1 regularization, and then take that subset of features and use it for a unregularized optimization. Something that comes up often when it comes to L1 regularization in Lasso, we rarely come to a problem with a preconceived notion of what value of lambda we want to use. Generally, it's the case that we want to try a bunch of different values of lambda and see which one does well according to training error, see which one promotes what degree of sparsity. Now, one way to do that is to apply the methods we used when we talked about zeroth order optimization. That is, we could just try a bunch of values of lambda, see what the values, we see what happens when you choose those values, and then decide accordingly. It turns out that we can do better. So to understand this, let's first look at the L2 regularization case. So that's what I'm showing here. I have the regularization weight on the horizontal axis, and again, this plot is structured where it has strong regularization on the right side, or sorry, a strong regularization on the left side, weak regularization on the right side. So again, this is L2 regularization, so we're not expecting sparsity out of it. So now observe that when we have weak regularization, we get large magnitude values for our parameters. And when we have extremely strong regularization, basically all of our parameters get set to 0. And then notice that in the middle, there's this sort of complicated interplay where the feature values go up and down, but in general, they trend towards having lower values. Now, let's contrast that to the L1 regularization case. So again, we have 1 over lambda on the horizontal axis. And again, we have large weights on the right side, low weights on the left side. Now, something interesting happens here. It turns out that when we apply L1 regularization with increasing strength, there are defined breakpoints where one feature gets set to 0, and it turns out that the values of the other features go linearly between those points. And in fact, we can compute analytically when all this stuff we can compute analytically. That is, what's the next feature to go to 0, and what's going to happen to the rest of the features, and how we can get this linear interpolation for the rest of the features. So this is called a regularization path, and it's an extremely powerful way of doing feature selection, because in kind of one step, one run of this algorithm, you can get the entire regularization path. That is, you can figure out what are the values of all the different parameters for all the possible values of our regularization strength lambda. This is very often a good thing to do. And for example, we can, if we have a specific number of features we want to be able to look at, as in terms of our feature selection, we can just follow the regularization path until we hit that number of features. And again, we just have to run that algorithm once.